Log on, tune in, find out. Another good idea from Cambridge.
We're going to remain in the spirit of mathematical geosciences. The next speaker is Prof. Wilkinson from British Geological Survey, located in Nottingham, in the UK.
Okay. Thank you very much, Darius, and thank you to Darius and for Andrew for the invitation to come and talk to you here today. I'm hoping after a slightly inauspicious start, nothing else will go wrong, so let's keep our fingers crossed. I'm going to talk about optimised survey design in electrical resistivity tomography and some progress that we're making towards implementing a time-lapse focused geoelectrical imaging system. The idea being to where you have a dynamic process within the ground, changes that are occurring over time that you're interested in. You want to focus the resolution of your instrument as much as possible on those regions. So before I begin, I'd just like to thank my collaborators, both at BGS, that's Phil Meldrum, John Chambers, Oliver Curas, Dave Gunn and David Noy, and also Meng Heng Lok from Geotomo Software in Malaysia, who designs and sells the resistivity imaging codes that we use. I'll start by describing the electrical resistivity, what the property means, why we're interested in using it, and also talk about, of course, about electrical resistivity imaging or tomography. I'll describe how we do optimised survey design, and also compare the results of the optimal designs against standard ERT surveys to demonstrate the improvements that we can see. I'll also talk about some practical implications of using these designs in the field. It's not quite as straightforward as we might first think, and illustrate this with some examples from a real field site. And finally, I'll talk a bit about the focused optimization that is the focus of our current research. Well, the electrical resistivity, it's an intrinsic property of the ground that describes the resistance to current flow. It depends on a lot of the parameters that geoscientists like to investigate. Just a few examples are, for example, the rock type, the chemistry that's going on in the ground, the hydrogeology, changes in saturation, those sort of things, changes in temperature. But it really is dependent on quite a few different parameters, which makes it a nice property to use as a proxy for processes that are going on within the ground. The idea of resistivity imaging is to try and find the resistivity distribution beneath the surface from measurements of the electrical potential either at the surface or possibly in boreholes. Just to give you a very simple example of this, if we imagine a homogeneous half space, so we have air above the surface, we have a constant resistivity below the surface, and we inject a current into the ground at a point via an electrode, and the current will flow radially outwards from that point just by the symmetry of the problem. And if we take Ohm's law and integrate over that hemispherical shell, we can determine what the potential is at a given distance away from the injection point. Now, rearranging this equation then would give us the resistivity in terms of the voltage and the current. Now, the point that's not terribly realistic here is that our electrode that completes the circuit is out at infinity, as is the electrode that we use as our reference potential. Now that's not terribly realistic for a field situation. What we tend to do is have our four electrodes reasonably close together. So we'll inject current and extract current from the ground on two electrodes, and we'll measure a potential difference on two others. That potential difference will be given by the expression there on the screen, where the distances are distances between the pairs of current and potential electrodes. We rearrange that to give us the resistivity in terms of the potential difference, the current, and this factor K here, which is known as the geometric factor, which just depends on the relative spacing of the electrodes. Now, in the homogeneous half space, this quantity is the actual resistivity of the ground. But realistically, of course, the ground isn't homogeneous, and in that case, we call this quantity the apparent resistivity. And in its very simplest form, as resistivity mapping used to be practiced, you would take a constant separation of your electrodes, and you just move it across the ground, mapping the resistivity out at many different points. The other thing you could do is to expand the configuration outwards, in which case the current penetrates deeper into the ground, so you get information about deeper depths, which was called resistivity sounding. These days, though, we have instruments that can do a lot of the work for us. We lay out, for example, a line of electrodes. This is from our research site, which is on an active landslide. We have a line of electrodes going from the toe of the landslide all the way up to the top of the hill. My colleague here is using one of our resistivity meters that's connected to that line of electrodes, and it's making multiple measurements on that line where the potential and current electrodes are selected automatically in different locations and at different spacings to give us an idea of the resistivity distribution beneath that line from the top to the slope down to the toe of the landslip. We can also take the concept a little bit further. If we want to do monitoring, then it's ideally we don't want to have to go back into the field continuously, so we install permanent arrays of electrodes. We can put these in either just below the surface or perhaps in boreholes, and we have an automated resistivity instrument that makes measurements on these electrodes at set times and in set configurations, and then transmits the data back to us so that we can analyse and image it. This is an instrument we've designed, a concept and instrument we've designed at BGS called ALERT, which stands for Automated Time-Lapse Electrical Resistivity Tomography. And you'll find if you follow our research at all that we use an awful lot of acronyms, and we tend to like them at BGS. Now, to image the subsurface, we need to solve an inverse problem. Of course, the forward problem is easier, so I'll talk about that first. In the forward problem, we know what the subsurface resistivity distribution is, we know where our electrodes are, and we want to calculate the potentials. Well, we just have Ohm's law. We have the definition of the electric field in terms of a potential gradient. Combining these, we get a nonlinear Poisson equation, which for realistic situations we have to solve numerically, typically use finite difference or finite element methods. And of course, you have to solve this with the appropriate boundary conditions. That's continuity of the potential, continuity of the normal component of the current density, and the potential goes to zero at infinity. The inverse problem, that's where we have many measurements of the electrical potential, which we scale to call the apparent resistivity, as I mentioned before. We want to deduce what the subsurface resistivity distribution is. We can't find this exactly. We only make a limited number of measurements of the potential in discrete locations. If we have a priori information, we can incorporate this in the inversion. Say, for example, if we know where geological interfaces are, or we have direct measurements of the resistivity from borehole logs, for example. But generally, we have to apply some global model constraints like model simplicity, model smoothness to the problem. So the problem is under and over determined. It's ill posed in the absence of the constraints. So we want the upshot is that we have to find best fit solutions, of course, that are compatible with those constraints. The way this is done is the problem is linearized, solved with a Gauss-Newton type approach. This is called the smoothness constrained linearized solution. The matrix G there is the Jacobian matrix, which contains the logarithmic sensitivities of the data to the model parameters. The model parameters are the model cell resistivity values. C is the constraint matrix, that's got the damping factors and the smoothness constraints. R is the model parameter vector, which is on a logarithmic scale again, as is the data misfit vector. And of course we iterate, we have a nonlinear problem, so we iterate the solution of this until we converge to some predetermined criterion. Now, all of this implies that we're going to have limited spatial resolution, and in fact the resolution tends to drop off roughly exponentially as you move away from the electrodes. But given that, if we have a given number of measurements, which is equivalent to survey time, survey cost within the field, we want to know what's the best combination of measurements we can make for a given survey size. Now, the number of configurations, number of 4 electrode configurations, scales as the 4th power of the number of electrodes, roughly. So for 32 electrodes, you've got something like 100,000 unique electrode configurations. And of course we can use any of these in any combination that we like. So the idea is to find a good set of configurations to use for our survey. Now, the standard designs that have been used for many years and their resolution properties are well understood, and they do quite a good job, but we want to know if we can do better. The way we assess our survey designs is via the model resolution matrix, which is defined simply by the relationship between the true resistivities and the resistivities that you get from the fitting process. The matrix is this matrix R. It's effectively a filter by which the inversion process sees the resistivity distribution within the ground. So the matrix R contains the information that quantifies how well each resistivity cell can be resolved by the measured data. In the linear approximation, it can be written in that way, and to simplify things, we just use the leading diagonal of the matrix, which we call the model resolution. This takes values between 0 and 1. 0 is unresolved and 1 is perfectly resolved. So to give you a quick example, let's say we have 30 electrodes equally spaced along a line. We want to look at initially at all the measurements we could make. We're going to leave out ones that would be potentially noisy. Those are ones that would return a very small voltages, and this leaves us with what we call the comprehensive set, and in this case it has just over 51,000 possible configurations. That's the plot of the model resolution for the comprehensive set. It's on a logarithmic scale here. Blue is very well resolved, white is very poorly resolved, and the resolution drops off roughly exponentially with depth, which is typical for a surface survey. So if we're going to assess a particular survey design, what we want to do is look at how well it compares to the resolution for the comprehensive set, because that's as well as we can possibly do. So we just plot the model resolution divided by the resolution of the comprehensive set, call that the relative resolution, and that's a distribution for a very small set of what we call dipole-dipole measurements. I'll come back to this in a few slides' time. So if we're going to design a new survey to try and improve on the standard surveys, the question we're going to ask is, if we start off with a small set of configurations, we're going to look and see how we pick another one that will improve the resolution that we're getting. So we want to find out at each stage which is the best configuration to add in to our survey design. We're going to do this by having a look on the effects on the model resolution. We want to maximize the model resolution. If we recalculate them directly, of course, then that's not going to be terribly efficient, because it takes order m cubed steps for each configuration, where m is the number of resistivity cells. So we use a rank 1 update to the model resolution matrix, the Sherman-Morrison formula, which takes order m squared steps and makes the problem tractable. That's the Sherman-Morrison update formula. I'm sure most people here are familiar with that. The vector G is the sensitivity vector for the additional configuration that we're testing. So we recalculate the change in the diagonal components only, so the whole process then scales as m squared. We do that for each configuration, and we rank the configurations in order of how much improvement they make to the model resolution throughout the image space. So if we start with a small base set, say a small set of these dipole-dipole configurations, then we calculate the resolution of that base set, assess the change that each configuration would make if it were included in the set, choose the top few best configurations to add in, incorporate those in the set, and go around the loop essentially until we've got enough configurations in our survey design. It's a local as opposed to a global optimization procedure, and we recalculate the resolution matrix only after we've added a group of cells to basically to save time, we don't accumulate the Sherman-Morrison updates. We do a recalculation of R every now and again to make sure that we don't run into numerical instabilities. So an example then, on the left-hand side, this up left corner, that's the comprehensive model resolution I showed earlier. This is our target that we're going to try to image. We have a uniform half space apart from these inclusions, which have a greater resistivity. So we run this animation. On the top right here, what we're seeing is the relative model resolution. That's the fraction of the best resolution we can achieve. And the bottom is the actual recovered image from the inversion. If we run this through again, we're seeing that the resolution is increasing throughout the model space until we get to a point where we have roughly 90% of the comprehensive resolution. And at that point, we're just about starting to see the very deepest block here. The other blocks have become well resolved by this stage. As I said, we're getting something like 90% of the relative resolution, and we're doing this for less than 10% of the total number of configurations. Just to quantify the algorithm performance slightly, this is in terms of the average relative resolution across the model space, which we call S. The dotted black line here is the results you get if you added configurations one by one and recalculated the model resolution at each stage, which is a fairly slow process, but it's probably the best we can do with this sort of optimization procedure. The algorithm that adds in the configurations by groups, which we call the compare R algorithm, is approaching this fairly well. But the important point that I'd like to point out is that the optimized survey, given by this green point here, is doing a fair bit better than the standard dipole-dipole survey, which has the same number of measurements. So let me just show you this. I probably should have put this picture on a little bit earlier. I've been talking about these dipole-dipole configurations. This is what they look like. You have a line of electrodes. You have a pair of current electrodes, which are separated by a distance A. You have another pair of potential electrodes with the same separation. And the interdipole spacing is an integer multiple of that separation. So for a 32 electrode array, we're looking at n values of 1 to 10. A is 1 to 4 unit electrode spacings. That gives us 575 measurements. This is the top left here. This is the comprehensive model resolution plot for that line of 32 electrodes. This is the relative resolution that you get from the dipole-dipole survey, and this is the relative resolution you get from the optimized survey. So hopefully from that picture you can see that the optimized survey is producing better resolution throughout the model space. It's of the order of 70% throughout the space, but of course the real test is actually inverting some data with them. This is our model target again. This is the image that you get from the dipole-dipole array. This is the image from the optimized survey. Now, I'm hoping this is coming out nicely on the screen. These two blocks here and here seem to have roughly as well resolved between the two surveys. This block here has better contrast in the optimized survey, and the very lowest block, hopefully that's reasonably clear, is it's not terribly great, but it has slightly higher contrast and it's a little better resolved than it is in the dipole-dipole survey. So it seems to be working quite nicely. Now what we haven't done up till now is really taken advantage of how the resistivity meter works. At the moment the procedure has been working in what we call single channel operation. That's measuring one potential difference for one application of current. But that's not very efficient. The resistivity meters are multi-channel instruments. They can make multiple potential measurements for every current pair. The one that we use, the meters we use at BGS, they take the form, the configurations are measured in this form. You have a pair of current electrodes, and then for that current injection you measure multiple potential differences. So we have a 10-channel system, so n is 10, and we measure these 10 potential differences. So you measure a difference between P1 and P2, a difference P2, P3, and so on up to Pn plus 1. So we have to adapt the design procedure slightly to take this into account. It works in pretty much the same way. You calculate the base resolution, assess the configurations. You then choose n, where n is the number of channels of the best configurations that actually also fulfill the combination criteria. So, for example, they have to have the same pair of current electrodes. You then add that new command to the base set and iterate the process as before till you have enough commands. So let's have a look at the results of the multi-channel algorithm. We're going to compare this with a single channel to start with. Now, there's more constraints on the multi-channel selection process, so we wouldn't expect it to do quite as well as the single channel, and it doesn't, but it's not far off. Now, this is for a multi-channel design with the same number of configurations, 575, but they're making as efficient use as possible of the multi-channel nature of the instruments. They're packed into 58 10-channel commands. And what we're seeing is that we have an average model resolution that's only about 2.5% lower than that of the single channel, and the images you get are fairly similar. Now, the other way to compare is we designed our single channel survey to compare with the dipole-dipole survey. The dipole-dipole survey doesn't make as fully efficient use of the instrument. It takes 98 commands to represent the dipole-dipole survey, so we're also going to design a multi-channel survey with 98 commands as well. So we have 98 commands, full usage of those commands, so we have 980 configurations, and in this case we're getting better resolution, about 5% higher average resolution, and also, again, I'm hoping that you can see that it's not too bad. The contrasts of these lower blocks, particularly this one, are somewhat higher than in the single channel image. So again, this seems to be working quite nicely. So these have all been synthetic examples. I want to show some examples with real data. This is from a site we've permanently instrumented with a resistivity monitoring system. It's an active landslide. It's near Malton in North Yorkshire in the UK. We've installed 5 arrays of 32 electrodes each along an active area of the landslide. The point of the monitoring is we're looking for the resistivity signatures of hydraulic changes within the subsurface that could be precursors to slope failure and the landslide slipping. This is our alert system. You'll notice that it's powered by renewable sources. It's wind and solar. This is one of the reasons why it's important for us to make use of the multi-channel capabilities of the system, because you're only putting a tenth of the total current, the total power into the ground that you would do if you did the survey in single channel mode. So on days, I mean, this was taken on a photo taken on a very nice day, but on days where it's misty, the wind isn't blowing, the sun isn't shining, the batteries won't last very long if you drive them too hard. So just to give you a brief cartoon of how the system works, we upload command files and the measurement schedule to the device. This then sets running, measuring the various configurations at the appropriate times. Once it's done, the data is sent back, it's stored and analysed at BGS, and the results are made available in terms of resistivity images on a website. So just before I go into the details, I'd like to show you the context of the resistivity images. This is the topographic surface at the landslide site, and the resistivity images are embedded in it. I'll just set this going in a couple of seconds, but you have these 2D images and a 3D imaging volume there. So let's set that in motion. The 2D images are from reconnaissance surveys that were done a few years ago. The 3D volume is alert data from the system. They're all on the same colour scale, so the blue colours are low resistivities. These are associated with mudstone formations at the site. The warmer colours, the greens through to the reds, they're higher resistivities. They're associated with a sandstone formation. and the upper mudstone layer is less competent than the sandstone, and it's slipping down the hill. The area we chose to install the permanent arrays actually covers 2 of the active lobes of the landslide. You can see them clearly in this ISO surface here. These are the edges of the lobes where the mudstone has slid over the top of the sandstone. So we're just looking in a little more detail. This is a slice through one of the 3D imaging volume. What we've got, as I mentioned, we have 2 mudstone formations. This is known as the Redcar mudstone. This is the Whitby mudstone. These have low electrical resistivities, and the higher resistivities are indicative of the Staithes sandstone formation. The Whitby mudstone here has slipped over the top of the Staithes. That's the origin of these lower resistivities at the top of the image. Now, there's a couple of things I'd like to point out about the image. One of them is that this lower boundary here, this lower geological boundary, isn't terribly well resolved by the image, which is a point we'll come back to in just a little bit. The other point is that the misfit error between the inverted data and the measured data is very good. Typically, depending on the noise levels at the site, we might be happy with misfit errors of a few percent. So 1% gives us good confidence that we've got good quality data, and that we're capturing the geological structure nicely in the image. So that's from one of our standard surveys. That's for a dipole-dipole survey. So I now want to look at the optimised survey to have a look at how much of an improvement you get, and frankly, it's terrible. We have misfit errors of about 40%, and the image bears no resemblance whatsoever to the geology, which was something of an embarrassment when we saw the results. The reason this is happening, I mean, we know that the hardware's working. We know that the electrodes are good because we're getting decent results for the dipole-dipole image. The reason we're getting this is because of an effect called electrode polarization. This is where, if you use metal electrodes to pass current into the ground, you then go and measure a potential on them later. Charges have built up on the surface between the metal-earth interface, and that gives you errors when you then use a charged electrode later on to measure a potential. There's 2 ways around it. You can either use non-polarizing electrodes, but they cost a lot of money, or you can try and arrange your measurement sequence so that you give the polarization a chance to decay before you use a charged electrode to later measure a potential. The decay times tend to be of the order of tens of seconds to a minute or 2. You'll notice that the dipole-dipole survey didn't suffer from these problems. The reason for that is that you can organise it in such a way that you never actually use a charged electrode to measure a potential. So we have our electrodes numbered 1 to 32 along a line. We measure we inject current on a pair of electrodes, say over here, and then the current electrodes are arranged in ascending numerical order. The potential electrodes are always higher in that order. So you have your current dipole over here, you have your potential dipole somewhere over to this side, and as you move your current dipole along, all your potential dipoles that you're measuring are over to this side, so you never actually use a charged electrode to measure a potential. But you can't do this nice ordering with a general survey. If we have a look at the command sequence from our optimised survey, we can see here the very first line in the command sequence, we're using electrode 1 to inject the current, and then 2 commands later it's being used to measure a potential. That's about 15 seconds. It's not really enough time for the charge effect to decay. The next command line, electrode 15 is being used, and that's used in the very subsequent command line to measure potential. Space maybe 7.5 seconds, and similarly throughout the command sequence. So there's a couple of ways that we could go about this. We could try and include design constraints to avoid this polarization effect into the original design algorithm, but we figured that was probably going to be counterproductive. We didn't want to put too many more constraints on the configurations it could select. We wanted to try and get the maximum amount of image resolution out of that process. The other possibility is to, once you've got your survey design, is to try and rearrange it so that you minimise the chances of this polarisation effect occurring. To try and quantify this, we wrote down a cost function for a given sequence to try and quantify how much problem it was likely to have with polarisation effects. This is just the sum of the reciprocal distances between using an electrode to inject a current and between subsequently using it to measure a potential. So what we want to do is to reorder the command sequence to minimise that cost function. I'm going to show three different approaches to this. The first one is simply just to randomly reorder the array, effectively shuffle the order of the command lines. The second is to use reorderings of the command sequence that are known to work well in the travelling salesman problem, which I'm sure everyone's familiar with. And finally is then to apply a global minimisation technique using those efficient reorderings to try and achieve the minimum cost function that we can. So just randomly shuffling the command sequence, we don't do very well in reducing this cost function. So we've got many thousands of iterations, and as you can see, the cost function isn't reducing very much at all. The more efficient reorderings that you sometimes use in the travelling salesman problem, the first one is to take a randomly selected section of the sequence and just shift it to another point within the sequence. We found that the optimal section length to move here was only one command, so effectively we just take one command out of the sequence at random and put it in, reinsert it somewhere else. The other rearrangement that you can do that tends to reduce the cost function quite efficiently is to just take a section and reverse it, again picked at random with a random length, and we found that the optimum length of the section to reverse was about 7 commands in this instance. So combining those two together, we get the red line, which very rapidly finds a much lower cost function. Now it's going straight downhill. We always pick new sequences if they provide us with a lower cost. If simulated annealing is somehow analogous to the thermodynamics of slowly cooling down a molten metal, this is closer to quenching the metal. So the metal would wind up in a polycrystalline state that didn't achieve its lowest possible energy configuration. The results from simulated annealing produce somewhat better results, somewhat better lower cost function. The simulated annealing, of course, lets the problem escape from local minima by occasionally taking an upward step. It reduces the size of those allowed upward steps as the iterations proceed, and these, like I said, it produces a somewhat lower cost function. It's worth doing even for this number of iterations. The process only takes less than a second, so in terms of the survey design, it's not critical at all. It's worth doing this. This is the separations between usage for current and subsequent usage for potential measurements for a randomly designed survey. You can see in the initial design we have an awful lot of separations of just one command, which would cause an awful lot of potential polarization problems. If we look at the random reorderings, it doesn't really help the problem very much. The quenched solution is a significant improvement, and the annealed solution is better still. In terms of our optimized survey, just going back to that, we can see that the separations have significantly increased. Here we have a separation of 10 commands. On the next line it's 10, the next line it's 9, the next it's 13, and so on. So we're getting separations in time of the order of minutes, which is what we want to do to minimize the polarization errors. And that's the CP separations for the reordered optimized survey. So this is finally we've got to the point where we can compare the standard image with the optimized image. In both cases we have low RMS errors of the order of 1%, but the nice thing about the optimized image is we're getting much better resolution here of this lower geological boundary. We have somewhat better resolution of some features up in the top right here, which are associated with cracking near the main scarp of the landslide. And we also find that the features within the images seem to have slightly better resistivity contrast in the optimized image than in the dipole-dipole. So I want to talk now about these were survey designs for monitoring with a fixed survey. What I want to talk about now is the possibility of focusing our survey design onto changes within the surface. This is, again, with our love of acronyms, this is something we've christened SMART, or Sensitivity Modulated Adaptive Resistivity Tomography. It's going to be based on the ALERT hardware, and we're going to look for differences between time-lapse pairs of images where changes are occurring, and try to increase the model resolution in those regions of the model space without adversely compromising the background image. So the system will look very similar to the ALERT system initially. We'll have data measured in the field, sent back, inverted to form an image. We'll then use the same survey design to take the next time slice, and we'll look for changes. So let's imagine here that this section of the image is going to decrease in resistivity for some reason due to some process. So we get a new image where this resistivity is decreased. We then look for the changes. We calculate a change mask, which simply has a value of 1, where there's been a significant change in the image, and 0 where the image is effectively constant. This change mask is then transmitted back to the system, which uses it to focus the design of the survey for the next time step. We want to test this in using a real system with a real problem, but in a controlled environment. This is a test cell that we have at BGS. It comprises a 6 metre long volume of well characterised and very uniform sand. It's 1.5 metres wide, 1.6 metres deep, and it's instrumented with a surface array of electrodes, and also with electrodes in boreholes. And on top of that, we have multi-level samplers which can directly sample the water within the cell to tell us to allow us to calibrate the images. What we'll do in this cell is to inject salt water, which is conductive. This will form a nice electrical contrast, and we can image the progress of this salt water tracer through the cell as it flows from one end to the other along hydraulic gradient, which you basically set up by pumping water into these injection boreholes and abstracting it from the other end. Now we've done some imaging a few years ago using the borehole electrodes rather than the surface ones, but we're going to use the data from these imaging to set up our basic algorithm for focusing our surveys. What we want to do is to look for changes between images. As I said, we will determine if a group of cells have changed significantly with respect to the background noise levels. To do this, we model the cells as independent and identically distributed variables. We found that the noise statistics had roughly Laplacian distributions with a mean of 0 and a standard deviation of sigma. And under the hypothesis that the group of cells hasn't changed, if you have n cells within the group, then this sum of the scaled absolute changes, they're scaled by the standard deviation of the noise as a gamma distribution. It's got a shape parameter of alpha, a scale parameter of 1 over root 2. So we conclude that a cell group's changed if this statistic is significant at a given confidence level. In our case, we're going to choose 0.1%. And we repeat over the whole image to give us basically give us our change mask. So this is an example. These are from the borehole imaging test we did a few years ago. We're going to select a group size of the cells of 3 by 3. The background noise levels are determined from a region where the tracer didn't reach within a certain time, and the changes had a standard deviation on a logarithmic scale of about 0.1. These are the statistics of the changes in the Laplace distribution. So the top image, let me run this animation through. The top image here is the conductive tracer, the blue colours passing through the cells. The middle image are the absolute changes with respect to the background, the baseline image, and the bottom image is the change mask calculated from those changes. So it's change masks like these that we'll use to try and focus the survey design. What we're going to do is we're going to rank the add-on configurations similarly to before, but we'll use a weighting on that ranking for each cell, which will depend on the change mask. If the change mask is 1, so it's determined that that cell has changed, then we'll use a weight of 1. For unchanged cells, we'll use a smaller weight, which will determine effectively by doing a few numerical tests. These are the resolution plots again for the dipole-dipole and static optimized surveys. We have an example change mask here on the right. This would be a focus survey with a weight outside for the unchanged regions of 0. As you can see, we're dropping off in terms of the image resolution somewhat compared to the optimized or dipole-dipole survey, so this is probably too much focusing. 0.5 seems to be significantly better in the background. At 0.1 and 0.2 you're starting to lose the focusing effect somewhat, so we figured that 0.5 was around about the best weighting to use. And this is just a simple example of how the focusing procedure would happen. We'd start off with a static optimized survey, which has this resolution distribution, and we use that to measure our resistivity data and invert to get our resistivity image. Again, the next step, we use the same survey design. We have a new resistivity image where we've got some saline tracer, a conductive tracer appearing at this injection point. We then take the difference between that image and the baseline to give us our change mask. We focus our survey design for the next time slice onto that change mask and produce the new image, which is then used in conjunction with the baseline. You can see how this is going, produce a new change mask, and so on and so forth. And finally, this is the last slide of results that I'm going to show. This is a simulation of how that would work using a model of the tracer flow through the cell. Now, this is fairly hot off the press, so it's maybe not the best example we're going to come up with during this project, but I hope it'll at least give you some idea of what's going on. So we have on the left-hand side here, we have resistivity images, similar colour scale again. Blues, cool colours are conductive, reds, the warmer colours are resistive. And on the right-hand side, the differential images, the white is no change, and where it goes blue, that's a change towards more conductive region, presumably where the trace is going. The top images are the simulations. That's effectively the true resistivities. Below that, we have dipole-dipole images, then static optimized, and finally the focused optimized images. So let me run this forward. You'll see initially that there's not a huge amount of difference, which is a shame. I was hoping for something really visually obvious here, but there are some differences that we can show. Let me just stop this at the appropriate point. Here we've come to the region where the dipole-dipole sensitivity is starting to drop off in this region here, and you can see that there's distortion of the recovered shape of the tracer plume. The static optimized image shows somewhat less distortion, and the focused image again a little bit less, although we're not seeing as much of an improvement as I might have hoped. If we just run through a couple of images further, you can hopefully see here that the focused image has very slightly better, slightly higher resistivity contrast than that of the static, but again it's not a dramatic improvement at the moment. So for future research, I mean, we're hoping to improve the resolution of the focus surveys. Up till now the surveys have been designed assuming the prior distribution, prior parameter distribution of a homogeneous half space. Now that's fine for doing a survey in the field where you don't necessarily know what the resistivity distribution is going to be. I mean, that's after all is why you're out there imaging it. But for monitoring, we do have a reasonable idea of the resistivity distribution from our previous images. So the idea is we're going to use more accurate sensitivity calculations based on those resistivity images, which will hopefully improve the results from the optimised surveys. We also want to identify situations where these surveys we can expect greater improvements from these surveys. I mean, in the examples I showed you, unfortunately, the tracer passes right through the region of reasonable resolution for all of those surveys. So the results we were getting didn't show huge improvements. And we're also going to prototype the system using real hardware and measure tracer movement in the test cell. So in conclusion, then. We've used a linearized approximation for the model resolution to assess image quality for ERT surveys, and this allows us to design near optimal surveys to get near optimal image resolution using a small fraction of the total possible electrode configurations. We've got algorithms that generate these for us, and we know that the optimized surveys tend to perform better than the standard designs, both with synthetic data and real data. We've also adapted these to use our multi-channel capabilities of the instruments and found ways to avoid the polarization problems. And we've made some progress towards implementing this focused imaging system, but we have further to go, and I'd be interested in any suggestions people might have to improve the results we're getting. Finally, there's a list of a few of our papers there, and if you're interested, you also should check out the work of Hans-Rudi Maurer's team at Zurich, who basically started us down this route of optimized imaging. So thanks very much.
Well, we have time for some questions. At the beginning, you showed us the partial differential equation, which is Poisson's equations, nonlinear. Is it the best model here? I think it results for some physics behind the phenomenon. But,
that's right. That's the physics of the forward problem essentially. So
is the nonlinearity inherent in this problem?
Yes, the current distributions depend on the resistivity distribution within the ground. So it has to be a nonlinear inversion process, I think.
When discretizing it, to use finite element method?
Finite element. We use finite element method if we have surface topography. We tend to use finite difference if the surface is fairly flat, just because it's faster.
I wonder if this polarization effect produces a bias in the measurement, right?
Yeah.
You could model that and subtract it and correct for it, couldn't you?
It's difficult. It's very dependent on the ground conditions as to how much of a polarization effect you're going to have. So without a lot of prior knowledge at the particular survey site, you wouldn't necessarily know the magnitude of the effect, I think.
So I didn't understand in the example where you ended up using some simulated annealing. I didn't understand why you didn't just put the constraints directly into the optimization problem.
I think it might compromise the results we get from the initial local optimization to design the sequence. I mean, it would work, I'm sure, but I don't think you get as good image resolution. In fact, you wouldn't. It would limit the freedom of the algorithm to choose the configurations just in terms of the image resolution. We want that part of the routine to focus on image resolution as much as possible, and then come back to it and then we come back to it later and just reorder, which seems to work well enough. So that's the route we chose.
The optimized, the focused results at the end.
Yeah.
The test region looks quite small. Is the reason that you're not getting such a difference that a lot of the sensors are actually sensitive to very relatively large volumes, so it doesn't matter so much how they're oriented or positioned? Can that be the reason?
Sorry, I don't think I fully understand
the actual
your
test
question.
is sort of the sand body is
Yes.
relatively small.
Yeah.
So actually I missed sort of what sort of volume your sensors, each measurement is actually sensitive to. But
Well, I mean, typically the sensitivity patterns it's not uncommon. You don't have to have a very long distribution of your sort of distance between your end electrodes for the sensitivity patterns to be covering most of that space, for example. There's an awful lot of overlap between sensitivity distributions for the different configurations.
So can that be the reason why you don't see much difference between the sort of dynamically optimized one and
I mean, possibly. I mean,
the whole volume.
we may be getting up to the point where that we're doing as well as we can. It'd be nice to know more definitely that was the case. It's perhaps given the approximations we've made, I'm still a little concerned that there's something better we could be doing to improve things that I've not thought of yet or haven't tried.
Thank you very much, Paul, once again.